We've been talking a lot about optimization problems, and I have another optimization problem for you. So here's the scenario. Let's say we have some string, and I ask you to, this is a fixed amount of string, and I ask you to pinch two ends of that string. So let's say you have a hand right here pinching onto some string, and then let's also say your other hand is somewhere up here pinching onto the other end of the string. Now, again, that length of string is fixed, and what I'm going to do while you're pinching and holding onto the string is I'm going to throw a ring on this, and this ring is going to have some weight to it, and it's going to eventually settle at some point. So maybe that looks something like this. Maybe that looks something like this. There we go. Something like this. Okay, and that's our string, and here's our ring that has settled. Okay, give it some thickness. There we go. Okay, so that's where our ring is settled, and again, you're fixed here. You're not moving your hands at all, and this length of string is fixed. So when I come up to this ring, although you're holding the string fixed, I can come up and push and pull on this ring. And it would trace out a curve that would look something like this. If I were to push and pull on this string, this ring here, this ring would trace out a curve that would look something like this if I were to come up and push and pull on it. So the question is, can we find some information about where this ring settles? And can we set that up as an optimization problem to find that out? So why don't you pause the video? Again, a good first step is going to be throwing some notation on this whole diagram and situation here. But then after you have that, why don't you set this up as an optimization problem and try to find some information as to where this ring settles. All right. Assuming that you've given it a go, we need to throw some notation on this guy and start to mess around with, how can we describe what this ring is doing? How can we describe this curve here? So let's do that. Let's first describe this point. Again, it's fixed. So why don't we just call this the origin? Why don't we call this 0, 0? So that's 0, 0. Again, your hand is right there. It's pinching onto the string. It's not moving at all. And this point too, again, is fixed. So you can call this anything you want. Maybe we can call it AB. Call it AB. And although these 2 points are fixed, I said that I could come up and push and pull on this ring. So this point down here, we're actually going to call XY. XY. Okay, so now we threw some notation on this, and we said we could set this up as an optimization problem. And with optimization problems, again, we're trying to find the minimum or maximum of something. So what are we trying to find the minimum or maximum of in this regard here? If we want to figure out where this ring settles, are we finding a minimum or maximum? Well, we want to find a minimum, and you can just see graphically here that we do want to find a minimum. And what is that minimum going to be? That minimum is going to be right here. And again, if we were to draw a tangent line, we would get a horizontal tangent line. So we're trying to find the minimum of this curve here. And what is this curve using our notation? Well, this is probably the hardest part of the problem, but I hope to make it a little more clear for you as we go throughout this video. So this curve here is actually going to be y. Y is a function of x. It's going to be y as a function of x. You give me an x value, I'll give you a y value. And again, this is constrained to the length of our string. So as we move this thing along, we're constrained by the length of our string, and that draws out this curve here. So we want to find the minimum value of this function here, y of x. And where does that occur? Where do minimum values occur? Well, they can occur at either the endpoints or at a critical point. And in this case here, we can see just graphically that our answer is going to occur at a critical point. We can see that this point here where this ring settles is in between these 2 points where we're holding on the string, and that's good enough. Typically, you can look at limits or something to evaluate these endpoints, but just graphically, we can see that it's going to happen in between these 2 endpoints and at a critical point. And where do critical points occur? Well, it's going to be at the derivative, when the derivative of this function here is 0. So that is a major part to this problem here. Now, I really want you to feel good about, maybe you're still confused about this function being y of x. and what that all means. And I think what's going to help is describing, again, I've been trying to say, this length here of string is fixed, and that really constrains when we move this ring here, that the length of string actually constrains this ring to this curve. So let's get a grip on the length of string, and then we can talk about more about this function here. So how do we find the length, the total length of this string? We want to find the total length. We'll call that L. The total length of this string. We need to find this length and this length. So why don't you pause the video and try to find these two lengths. All right, assuming that you've given it a go. Again, maybe you can start to see that we could draw some right triangles here. That we could make some right triangles. We could get something that looks like this. That looks like this. Looks like this. Some right triangles. And then to find the hypotenuses of these right triangles, we need to get some lengths here, and we can use our notation to do that. So this here is going to be x, and this length here is going to be y, and then this length here is going to be b, and this top length here is going to be a minus x. A minus x. Okay? And then just by the Pythagorean theorem, we can find these hypotenuses. So we have over here, this is going to be x squared plus y squared. X squared plus y squared. And then over here, we're going to have what? We're going to have a minus x squared, a minus x squared, and then plus b minus y. Not b plus y, but b minus y. Y is negative. So we have b minus y here. And you could substitute some concrete values in and back substitute after you solve that out, and you'd find this to be the case if this doesn't feel good to you. But it is b minus y squared. So that's what we find for these two lengths, and then we add them together, and that's the total length of our string. So let's do that. So this is going to be x squared plus y squared. X squared plus y squared. And then we have plus the square root of a minus x squared plus b minus y squared. B minus y squared. And now what I hope to do, now that we found these two things, in the next video, all we're going to do is differentiate this length equation here and substitute in this condition for our derivative being 0. But I really want you to feel good about what this is saying, because in other optimization problems, we just give you an explicitly defined function. But in this case here, our function y of x is implicitly defined by our length equation. And what that's to say is, and I think this might really help, is if we were to draw the same situation, that we've been looking at, let me try to get a straight string here. Something like this, what we've been looking at so far. There is our ring that's settled. Again, if we're saying that our function here, y of x, is implicitly defined by our length equation, that's to say, again, as we push and pull it, we're just going to have new right triangle setups. So right now, we've been looking at this right triangle setup. Something like this right triangle setup. But again, we said as we push and pull it, it's going to trace out this curve. So let's just take the scenario. Okay, if we were to pull on this ring a little bit, our ring would be somewhere over here. And this length equation is saying, okay, we're just going to have new right triangle setups. So we're going to have these new right triangle setups. We're going to have something that looks, there's our string. And these are our new right triangles. There's a right triangle, and there's a right triangle. So all that's to say is that this function here is defined implicitly in our length equation. So as we push and pull on this ring here, we just have new right triangle setups. And those right triangle setups are, again, described by this length equation. So that's how these guys are related. And it's, again, all going back to this idea that this curve here is constrained by the length of string that we have. So this is the hardest part of this problem. And in the next video, all we're going to do is some differentiation, and then we'll substitute this value in, and we'll get some information about where this ring settles.